Hello there, I'm the Base Manager and welcome back to a design showcase / tutorial. Today, my friends, I bring you the CAN bus system. I took this straight from the automotive industry and I applied it into Oxygen Not Included to help us solve the automation spaghetti. Even though I created a little bit more spaghetti in the process, but oh well. Now, if you already know what a CAN bus line is and the CAN bus system is, or you just want to skip the explanation and the backstory, there is a timestamp right here. Future me over here, please, pretty please, over here. Okay, you see it? Okay, so if you want to skip it, skip to that timestamp. In any case, what is a CAN bus system, may you ask? Now, a little bit of backstory. In real life, I am a AutoCAD designer. I make manufacturing blueprints for car harnesses. It's pretty low-tier office job, but in it, you know, I get to see the insides of systems like this. And because, you know, even though I don't do any thinking, engineers do the thinking for us. I just do drawing. You know, because I have a couple of brain cells that still work, and I am curious, you know, over time you go and you pick up a thing or two, right? Right. Now, what is this in reality? You see, automation in automobiles works very similarly to Oxygen Not Included. You have a sensor, let's say a oil pressure sensor, right? The sensor is set up to a certain threshold. If that threshold is reached, it is going to send a green signal. If not, it's going to send a red signal, pretty much like Oxygen Not Included, right? Right. Now, as you might imagine, modern vehicles and engines, they do have a cornucopia of sensors: oil pressure, water pressure, temperature, air pressure, air humidity, oxygen in the exhaust, I don't know, flywheel position, camshaft timing, I don't know, ignition sensors, injection sensors, fuel pressure sensors, like, just name a few, just to name a few. Of course, there is so many I don't even know the English name for them, okay? But yeah, as you might imagine, when you have so many sensors, and usually the ECU for your car is located on the inside because the ECU is quite sensitive and the engine bay tends to be a bit toasty, so yeah. This requires a huge bundle to go from the engine bay into the inside of your car, which tends to be heavy, bulky, expensive, and, well, many things undesirable, right? So engineers back in the either late 80s or early 90s, I think, came up with a brilliant solution: the CAN bus system. What is this? Instead of having all of your sensors communicating directly to the ECU of your car, let's say this is the ECU over here, right? Instead of having all of these wires go from the engine bay and from the rest of your car, because you have other sensors, into the ECU, what you have instead is a encoder system. Similar to this one, but not really, much more complicated. This is a poor man's version. It's what I could come up with. What is this encoder unit? Well, pretty much all of your sensors are connected to this encoder unit, and this encoder unit will turn this analog signal that we have over here into digital, and that digital will then travel through two wires, which are usually twisted and with a wire mesh to protect from electromagnetic interference, right? And they will travel into the ECU. Inside of the ECU, you do have well, in older units. In newer units, they can already read digital signals, but the older units, you know, late 90s cars, for example, inside of the ECU, they usually have a decoder unit such as this to decode this digital signal back into analogs, right? They go like this, and then they have back a analog signal so that the ECU can read it and then act upon it. So yeah, this is the basic explanation of what a CAN bus is. The advantages is all of these wires can write over here at the same time, because it's no longer a yes or no signal, it's a frequency, right? And with frequency you can just transmit a huge amount of information that you could not do it with analog. So, with that out of the way, with that explained, how does this thing works? Well, it's quite simple. You have, like, this is going to be our input. This can be a myriad of sensors, right? This is what is going to represent our green signal, and pretty much the idea is to have this green signal turned into code. Please game, don't lag right now while I'm explaining. Turned into code, have that code written into the ribbon and then deciphered by a decoder unit, which will then turn this code back into analog over here. Now, this is just a self-resetting unit because, you know, for testing purposes, I don't want to be pressing reset all the time. As you can see, I have tested this thing quite a lot. Now, let's just do a quick demonstration. Now, I have to be honest with you, my friends, this thing is pretty fast. Okay, I'll do it at ×1 and ×3 so that you guys can see. Like, the objective is to have this, turn on this light. Game, please. Thank you. So, it writes the code is deciphered, and the light is turned on. And now the line is once again available to be written by another system. I duplicated this because this is not symmetrical. This is if you want to write into the right side, this is if you want to write into the left side, because, you know, things are not symmetrical, and so the disposition of bridges and whatnot is slightly different. But all the parts work the same, right? Right. And so, because now the system is empty, another thingy can write into it a different code that will then be interpreted by a different decoder, activating a different thing. Pretty cool, right? Right. So, yeah, now, I made this as foolproof as I possibly could. We have multiple things that prevent writing at the same time. This is why we actually only have 2 digits for our codes, because we actually need all the 4 bits of the ribbon for this to work. Bit 1 and bit 2 are the code. Bit 3 is the busy line. This bit tells all the encoding systems that the line is busy and is being written upon, so the other encoding systems don't write into the line at the same time, creating massive confusion. And then you have bit 4 over here, which is the confirmation/reset of the entire system. This is the signal or pulse that is going to tell the encoder system that the signal was received, allowing it to reset. Right? Right. Let's try to explain this, shall we? Now, my friends, I just made a small cut over here because I'm pretty certain I won't be able to explain this first try, so I need some space to make the editing. But in any case, so let's start the explanation. I will have to pause the game because this thing works super fast and there is no way I can explain it while it's working, and then we'll see it in action once again. But the green signal starts over here, and in here we have our very first safety system. You see, the encoder unit cannot handle a flickering, you know, your sensor going on and off, on and off, on and off all the time, because it's right there in the threshold, right? Let's say Atmos sensor, one of these, right? It's like there. It's the fluid is 499, 500, 499, so it's constantly flickering. We can't have that. That is going to send the system into haywire. That's why we have this. This is to prevent flickering. Flickering gets filtered through here, and the buffer guarantees a stable signal for at least 2 seconds, which is more than enough time to make the encoder unit do its thing. Then from here, this constant signal is turned into a pulse. This is a pulse generator. A pulse generator pretty much is very simple. You just have a memory toggle with a filler gate with a 0.1 seconds. This is going to allow a green signal to go through for a 0.1 seconds. Right? That's what a pulse generator is. Then the pulse sends the green signal into the second memory of the system. This is one of 2 turn on and off memory toggles. This is the safety memory toggle for, how should I put it? You see, if you have multiple encoder units writing at the same time, bad things will happen because the code will not be transmitted correctly. However, this will hold the signal in place if another encoder unit is writing. So you can call this the waiting memory toggle, right? Once the other units are fine, you know, have terminated their work, this signal will be allowed to pass through this AND gate. This AND gate is part of that same system. We will double around over here, but for now, the only thing you need to know is that this AND system, this AND gate allows the pulse to pass through if nothing else is being written on the ribbon. Alright, so nothing is being written, and that signal goes through the memory toggle, which we can call it the turn on and off memory toggle of the entire system. This is what allows the AND gate over here to start generating frequency. So this pack of AND gate plus timer sensor is what we are gonna call the frequency generator. This timer is set up to 0.1, so in theory it's going to flicker between green and red 10 times in 1 second, so I think that's like 10 hertz of frequency that we are using. So, you know, like, I'm not the most scientific of person, you know, I do what I'm told by the engineers, but so if I say any of these names of units wrong, you know, it's like I'm no engineer, so I don't have any obligation to know these kinds of things. But in any case, let's continue. No need for a tangent. So our frequency generator has been activated, right? So this is green and it's going to flicker between green and red, generating a frequency. From here we have 2 wires going. The first wire goes into the ribbons to start writing the frequency. The second wire goes into the signal counter, which is going to be our code setup. In here we set up our code. The code for this encoder is 57, as we can see. Right? Okay, now things get a bit complicated, my friends, because you see, we need a way to stop the frequency from writing into the specific bit whenever the number of signals, of pulses, has been sent. That's why we have these AND gates with these memory toggles over here, because in essence, this thing over here controls the turn on and off of the entire the encoder and the closing and opening of the gates for bit 1 and bit 2. So these things will count the amount of pulses. Once the set number of pulses has been allowed to go through, it's going to send a green signal into their respective memory toggles. These memory toggles are going to turn green, and those green signals will travel through these lines over here on the side. These lines will then go into these memory toggles, which is going to shut them off once they are green, and because these things got shut off, are going to send a red signal into their respective AND gates, closing the bit from being written upon. And then they are also going to travel through another AND gate over here. This AND gate is the reset or turn off AND gate for the entire encoder. Pretty much it's going to be twofold. It's going to generate a pulse over here and generate a pulse over here. This pulse will reset the counter, and this pulse will travel through this wire, resetting the memory toggle for the waiting signal and the memory toggle for the turn on and off signal. And yeah, once this signal has reached over here, the entire system has been reset and turned everything back to 0. All the things are shut off, and everything is cool. I know this is a little bit complicated, my friends, so in order to help you out set this up, I will provide you right now, future me, hey, future me, here, listen to this. Put the images right here so that people can look at them. So these images are available in my Discord server, links in the description, but if you don't want to go there, take screenshots of both the encoder and decoder setup. The decoder is pretty simple, the encoder is quite complicated. Okay? The screenshots taken? Cool. There we go. Now, one final thing on the entire system, we have an option. If you want, of course, this is completely secondary. However, I would vehemently advise you to do this. This is an error notification system. You just need to splice the wires, the bit 1 and bit 2, into an OR gate, and this OR gate will then communicate to a filler gate, which is going to wait 5 seconds to activate a notification thingy. This notification is going to tell you, hey, there is an error in system 1, or in system whatever you want to call it. It's pretty useful. However, just one thing, if this thing is correctly set up and you have an error in your system, If another encoder writes into the line and a bit 4 signal is received, the entire system will reset itself and the error will be cleared. So technically it's a self-correcting system, okay? You don't have to do anything. And now we come into the most important part. This is the biggest disclaimer. You need to listen to this. Please don't skip this part, okay? Very, very important. This thing generates the frequency, and the frequency is very, very, very important, because for some reason the game farts itself sometimes, because, you know, this thing is writing extremely quickly, as we can see, at times 3, even quicker. So the game from time to time will lock an input from here in place. However, because it's writing so fast, it cannot clear the lock by itself fast enough for a signal to be lost. So the lock will be kept in place, the entire system will lock down and wait for the timer sensor to stop being crazy. And if you do nothing, or if you pause and unpause the game, the timer sensor will stop being crazy, and the signal will continue to travel and everything will be fine. Nothing will go bad. Or if you just wait and do nothing, eventually the timer sensor will stop, and the signal will continue, everything will continue fine. However, do not under any circumstances put these two things to 0.2 seconds. Because for some reason, I don't know why, the game doesn't like it, okay? If you put to 0.2 and the game has a brain fart, the signal will actually be lost. The system will unlock itself. However, when it unlocks itself, that input which was stuck will be lost for some reason. I don't know. I thought that 0.2 would be better for the game, but the game doesn't like it, okay? If you really need to decrease the frequency for, like, for example, performance reasons, use 0.5 and then multiply all of these timings by 5. It's that simple. Do not, under any circumstances, use 0.2 seconds. You have no idea the amount of headaches I had to endure to come to that conclusion. I thought I had a timer problem. No, it's just a game problem. I don't know. Look, I tested the system 196 times at 0.1 seconds. 0 problems. I tested the system like 3 times at 0.2 problem. Like a million problems. Yep. No, don't use it. Okay? Now, with that warning out of the way, let's go into the decoder unit. The decoder unit, well, it's quite simple. Let's just watch it in action. Receives the signal, and then activates that, and that's it. Super simple, right? Right. Let's explain this thing. So you have bit 1, bit 2, and bit 4 over here. Bit 1 will write into the first digit, bit 2 will write into the second digit. The code has been established, right? We'll send a green signal into their respective memory toggles, which once the entire code has been deciphered, will activate this AND gate. This AND gate will allow the signal to go through momentarily, activating the final memory toggle, which will transform it back into analog system. Right. Then over here we have a confirmation pulse. That's why we have this pulse generator right here. This pulse generator will generate a small pulse into bit 4, which will confirm into the encoder that the message was received and will reset the entire thingy back to 0. Not only that, it will also reset the counters over here back to 0 and these over here back to 0. Now, it is very important that the reset for both the counters and the memory toggles comes from bit 4 and not from this wire, because if you have other systems right during this time, this is still going to read it. Like, for example, the code for this one is 3-8, right? So if I activate this one, for example, let's just wait for the buffer to go away. And bam, 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 here we go. You see, it still reads, but because the code is not the desired one, the signal will not go through, right? It's going to ignore it. However, because it's going to count it, it still needs a ping from bit 4 to reset itself back to 0. Especially because, let's say that this one was 58 and not 57. This would activate this one, but not this one. Or maybe it would, because it's... Oh! Darn it! Wow, okay, now this might be less than ideal, but okay. now that I come to this realization, but well, I'll probably will have to find a small fix for it later. But other than that, let's just continue, and then I'll just make another cut and put the solution over here. Now that you have your analog system, comes the final requirement for the entire thingy. The entire thingy must be self-reset, or you're gonna need two encoder units, one for the turn on and one for the turn off. But that's pretty simple. Let's say you want to transfer 150 kilos from this one into this one, right? You just put the valve right there and the timer of 150 seconds. We know that this thing travels at 1 kilo per second, 150 seconds, 150 kilos. This has a limit of 200 seconds, but hey, if you need more, let's say 400 seconds, you just need to put another one, 600, 800, 1000 seconds, like you just need to put as many fillers as you feel like it to keep your system active. Now, the good thing about this is the fact that, yeah, you can, like this could then like turn on and off as many times as it wants. This is still green, so nothing is going to happen. Now, let's go back into another thing, which is how do we prevent this system and this system from writing at the same time into the thingy, right? Let's just turn this off. For a moment, everything is turned off. Okay, so I pause the game, and I turn this on, and I turn this on as well. How do we prevent confusion from happening? That's why we have bit 3 over here. Now, it is very important, the bit 3, and everything in this side and in this side is precisely the same, except one thing. This filler gate, this is what we are going to call the priority setup, the setter or whatever. This is the priority thingy. In here, you are going to establish the priority of your system. This is a high priority system at 0.5 seconds. This one is a medium priority system at 1.5 seconds. So, what is going to happen whenever I activate... this is active, right? Sending a red. Okay, it's red. Oh, god damn it. Okay, let's try this again, shall we? The game is paused, everything is, you know, turned off. In fact, I have this thing over here. Let's turn on bit 3, which is a theoretical something, right? It's an encoder which is writing into the line, so everybody knows that they can't write into the line. So we activate this one and this one. They came online at the same time. Whatever was requesting something, it's now trying to request. As we can see, the signal gets stuck over here and it's not allowed to pass through. The moment the third encoder would stop writing, one of them is allowed to pass through, but not the other. The other is still in waiting mode, and now it's allowed to pass through. Everything is reset and back to square zero. So pretty much what you need to do is quite simple. As we established before, this memory toggle over here, the one that turns on and off the frequency generator, sends a signal into bit 3. So what you do is you have this wire that goes into bit 3, you put a buffer gate because the system becomes deactivated before the confirmation of ping 4. So you need this buffer gate over here with a little bit of time just to make sure that nothing is written before the ping 4 is received. That's why it's here, and in here it writes into bit 3. Now you make a splice over here into a XOR gate, XOR gate, XOR gate. One of these guys, okay? One of these, okay? And this is going to read from both the internal line and from bit 3. What does this mean? If both this and this is green at the same time, that means that I am the one writing, right? Therefore, this is going to turn red, which in turn is going to send a green signal through this NOT gate, allowing the AND gate over here to let the pulse from the waiting memory toggle to pass through. If, on the other hand, this one is green and this one is not, then that means someone is writing into the line, which will then turn the signal red, which in turn will not allow the memory toggle to let their signal through, keeping the signal in waiting. This is very important because otherwise multiple systems would be writing at the same time into the CAN bus line, and that would be a very bad time, let me tell you. Now, a little bit of troubleshooting. once again, at 0.1 seconds, there is very low likelihoods of you getting a wire in your system. In 198 tests, I never got a wire, never. But if you want to purge a wire from your encoder, just keep a signal switch into the ribbon 4 and just activate it. If you activate... come on, bro. If you activate this one... Oh, come on! If you activate this one, it's going to reset everything, and then, you know, you just need to make sure that there is no signal waiting over here, otherwise it can get confusing sometimes, not really most of the times, but yeah. If you go into A-wire mode, like I said, if you receive a ping 4 from other encoder, it's going to clear the A-wire from the system. But for some reason, let's say that you are not receiving anyone to clear the A-wire by yourself, by hand. You just need to ping bit 4 and everything is clear. Now, one of the great advantages of this is the fact that you don't, like, why would you need this? It's, well, my friends, it's because you can just run one of these wires throughout the entirety of your base from top to bottom and have all of your systems right into it, having all of information compiled into a single line instead of having multiple lines. This can then be transmitted into freaking space, which will then you then on the other side, because you know this is a test map, just in case you haven't noticed. I don't have any other planet available to me, but you know this. Let's say that this is on another planet. You can pretty much then continue your CAN bus line on another planet. So in theory, let's say that you have a power plant right here that needs natural gas. It sends a signal through the CAN bus system. The CAN bus system will then, you just need to rename your thingies, right? Will then send a signal over here, bit 1, bit 2, bit 3, bit 4, and then it's going to receive it. And then on the other side you do the same, right? So that you can write from the other planet into this one to tell it, hey, I received your thingy, you can shut off now. You need the bit 4 thingy as well. And yeah, you just can propagate your CAN bus line through the other planet and then throughout all of your planets. And then have all of your planets, all of your bases connected to a single ribbon line. 4 freaking wires, my friends. All systems writing into 4 freaking wires. That's unbelievable, if you ask me. Now, let's look at this thing up, because I really like to see it. Like, this works so fast, my friends. It's redonkulous. Okay, this is ridiculous. Look at this. Bam, bam, bam. It's done. It's done. Look at this. Oh my god. I just... This thing is ridiculous, my friends. I just love how these things operate. Look, let's see it through the automation side. Bam, 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 bam. It's done. I love it. But yeah, now there is a small issue that I just need to figure out. So yeah, it's pretty simple. I probably just need to put a filler gate over here so that it sends a green, constant red signal and a green signal and not a red signal. So yeah, just give me a moment while I fix this, because let's say this one is 57, right? If this one sends 58, I'm pretty certain, look at me, I'm troubleshooting on the spot. I'm pretty certain it's going to activate this one as well. Let's try it. I didn't thought about this before, okay? But let's just see if that is going to be a truth thing or not. So everything is ready. Could you please like reset itself? Could you please just reset yourself, please? There we go. So if I activate this one, this light can't turn on. If it turns on, then it means we have a problem. Yep, you see? We had a false signal, but that's fine. It's quite simple. We just need to put a filler gate over here, because it's then going to count from 7 to 8, which is going to break the signal, and the ghost signal is not going to go through. Okay, 1 second, please. There we go. Let's try with 0.2 seconds. And go. Let's see. 0.2 is still too fast. Aha! Timer discovered, my friends. Okay, at 0.5 in these filler gates, the ghost signal will not go through and will not activate this. Now, will it read its own signal, or is it too fast? I don't think it's too fast. Perfect! Problem solved, you see? Like, we had a problem and it's fixed. We only need to add these 2 things to the decoder. So if you like the blueprints that I placed on the Discord, because they're already there, they don't have this one. So yeah, keep this in mind. You need to put these thingies in here. Okay, let me just replicate it on the other side. Bam, bam. We then cut this. Bam, bam, and then 0.5 is all that it takes, my friends. 0.5. That's going to create a small delay in the entire system, but hey, now no ghost signals will go through. So yeah, my friends, that's pretty much it when it comes to the CAN bus system. I'm sorry if my explanation was a little bit all over the place, but as you can see, this thing is already a little bit all over the place by itself, so it's really difficult to explain. So if you have any questions, just go into my Discord. I will have the images that explains the timings, because all of these things have different timings, and if I'm going to go through all of them, it's going to be very complicated. It's easier to put it in an image with some side notes so that you guys can read it and set yourself this thingy. The only thing you need to know is if you want to change the frequency for some other than the one that I'm telling you to, just multiply all the timings by that increase. So if you have like 0.3, you multiply by 3. If you have 0.2, which I'm telling you not to do it, but if you want to do it anyway, just multiply by 2. So yeah, don't, like, why would you? Please don't, okay? It's like, it's the one timing that doesn't work. All other timings probably do. The 0.5 does work, because I tested it, but yeah, I'm not going to test like 5 billion different timings when I'm going to use this one. So yeah, don't, any questions, go into my Discord or in the comment section. I'll do my best to explain it. I will provide you with all the images, like take another screenshot of this one, please, by the way. Another screenshot over here so that you can see the connections, and another one over here so that you can see these connections as well, together with the explanation thingy. Should be all that you need to be able to set this one up. But once again, any questions, just let me know in the Discord or in the comment section. Besides, if you do end up using this and you do some crazy something with this, please show me. Go into the, like, you can drop an image in the Discord the section for oxygen not included. I'll be pretty curious. So once again, links in the description down below. But with all of that said, my friends, I hope that you have enjoyed this design showcase / tutorial, and I hope that you have learned something. If you have, please consider subscribing and help the channel grow. But in the meantime, this is the Base Manager signing out. Bye bye.